Hello everyone, welcome to today's ASRG webinar. My name is Sotirios Katsikeas from ASRG Stockholm. Before we jump to today's presentation, I'd like to tell you a little bit about ASRG. ASRG, the Automotive Security Research Group, is a non-profit organization founded a bit more than 4 years ago to support the development of the automotive security industry. We have developed a platform and a community for the automotive security industry, the academics and organizations to share knowledge, communicate, and build value with collaboration. This is a community for you, built by you, with a goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Moving to our today's guests, it is my pleasure to welcome Sotirios Katsikeas, a Ph.D. student at KTH Stockholm in Sweden, who is working on threat modeling focused in the energy domain, and Joar Jacobsson. Joar is the head of the cyber domain and process development department at foreseeti. He is responsible for designing modeling languages and developing the methodology of threat modeling and attack simulation used in securiCAD. In case you have questions during the presentation, please write it into the chat window. After the session, we will have some more minutes for a Q&A session. So, Sotirios, the stage is yours.
Thank you very much and welcome. So, as Nikolaos introduced me, I'm Sotirios Katsikeas, and today I will be presenting VehicleLang, which is a probabilistic modeling and simulation language for the vehicular cyber attacks. So, if we look on modern vehicles, we see the following typical elements found in a lot of them. So we first have the ECUs, the electronic control units. Those are actually embedded systems that are programmed to control parts of the vehicle. And they, of course, run programming code, which often is called firmware. But we also, in the last years, we also have the ability to update that firmware over the air, so it becomes more like a program that is running instead of the firmware. Then those ECUs should be connected somehow. So we have the vehicular networks. The main three actors here are first the CAN bus, which is the controller area network bus, the LIN bus, which is something like CAN bus, but for smaller parts of the network connectivity employed on the cars. And then we have a FlexRay network, and of course the vehicular Ethernet network. Then we also have gateway ECUs, which are more powerful ECUs that have the ability to bridge two or more networks because they need to communicate with each other to have complete control over what happens in the vehicle. And sometimes they also act like firewalls or intrusion detection and prevention systems. But this is something that doesn't happen typically. It's only on the advanced gateway ECUs that they have those abilities. And finally, the most important one, because it's internet connected, is the infotainment system. So it's the information and entertainment system of the car, and you expect from it to be able to connect on the internet to stream music or get information about traffic. But it also allows the users of the vehicles to control various functions of the car. So it's also connected to the internal networks of the car. So we can easily get that the modern vehicles, as I said, are connected to the internet. Most of them are continuously connected to the internet, and it will become worse in the future because we are also talking about vehicle to infrastructure or vehicle to vehicle communications. So all those are direct connections to the internet or to other vehicles on the road. We talk about a very large number of actually computers that are on the cars, the ECUs, and they are running the programs that are actually made of code, and they can have vulnerabilities. And a high number of networks is also involved in the cars. And last but not least, they are equipped with cyber-physical systems, like the ones that allow the car to not drive away of the lane when you drive on a highway, or that help you brake if you are in a city and the car in front of you brakes. So we are talking about systems that can take control of the car. Those are the cyber-physical systems. Taking all those as facts, we can really see that they create a significant danger in regard of security if they are exploited by attackers, or if there is some vulnerability on the code that is running on those ACUs. Now, all those were used as a motivation for creating VehicleLang, and VehicleLang is actually a way of modeling the infrastructures found on vehicles and probabilistically running simulations of cyber attacks on them. So the motivation can be seen from two sides. First, from the consumer side, it's the achievement of higher end user safety and trust to the manufacturer of the vehicle. And for the industry, the motivation is that they will have better cyber attack resilience and an attack-proof design. So taking those two aspects as motivation, the goal was to create the language, the VehicleLang, that will be able to model and simulate such attacks. And the goals of the first for the first ever version of VehicleLang was to cover all the basic vehicular components using a bottom-up approach. So starting from the very internal networks and going up to the external parts of the vehicle, and also to cover the all so far known attacks that can happen on those components and networks. But before we get into detail, let's briefly talk about the theory. So we're using probabilistic threat modeling. So what is threat modeling? Threat modeling actually is a process that allows the identification, enumeration, and prioritization of potential threats in a system. But if we talk about the probabilistic aspect of it, then we can say that the likelihood term is introduced. So the attacks that we would like to model, and we will get simulation results on them, require some effort by the attacker. That effort is expressed with the use of probability distributions. So it can be easy to achieve, hard to achieve, or it can be easy to achieve after a specific amount of time. So we are starting to talk about time to compromise of specific assets or specific attacks that we are modeling. So we have the two terms, the global time to compromise, which is the time the attacker needs from the entry point to reach the end goal, which in the vehicle could be, for example, taking control of the steering wheel. And then we also have the local time to compromise, which is the time needed to move to the next step needed to perform the whole attack. Then, if we talk about the simulation results, we are interested in the shortest path, which is the path that the attacker has to follow to be able to compromise the end goal while having the lower time to compromise. So it's the fastest the attacker can go there, the better for him. And of course, the higher the time to compromise is, then it also implies that it is less probable to succeed, because many of the attackers do not have an infinite amount of time available to perform the attack. So that's the theory. Now, we're still on the theory part, but we're getting more to the practical sides, because in order to achieve this, to create the probabilistic simulation language, we are using MAL, which is the Metatag language. And this is I would call it a framework, or we can call it a meta language, which is proposed by professors at KTH on 2018. And since it's a meta language, is actually a way to create attack graphs, but not having to repeat the whole procedure every time you want to create a new attack graph for every new use case, or even for domains that are similar with each other. So it specifies the rules and the elements for the domain-specific languages that are going to be developed. Thus, it makes the modeling of new domains easier, allows the reusability of elements, and of course, exploits attack graphs for the simulation results and probabilistic simulations. So what are the main elements of the Metatag language? So any MAL-based domain-specific language will include the following basic elements. First, we have the assets. Those are the basic components that are found on the domain we want to model. In the case of the vehicle, it will be, of course, ECUs, networks, most probably some sensors and actuators and stuff like that. And MAL allows also inheritance between assets. So you can have, like the example of gateway ECU and ECU, we can have inheritance. So gateway ECU will be inheriting from the ECU asset because it is what a typical ECU is, and it also adds some new functionalities and new attack vectors, most probably. Then we also need to have connections between the assets, because without connections, we will not be able to create models. So those connections connect the different assets of the model so that the actual infrastructure is being replicated, and we call them associations in MAL. Then we have the attack steps. The attack steps are, as the name suggests, the steps needed for one attack to be completed by the attacker. So it's one attack vector, if you like. It's comprised of many attack steps that can spread among different assets. So you start from the network, and then you reach another attack step on maybe a neighbor network, and then you also can reach another attack step on the ECU to perform an attack that is, for example, controlling the ECU. So those attack steps can be of two types in MAL. It's the AND attack step and the OR attack step. The difference here is actually what is needed for you to move further. So if we're talking about an OR attack step, you just need to be able to compromise at least one of the previously connected attack steps. While if we talk about an AND attack step, let's say you have attack step A, which leads to attack step B, then to go from A to B, you will need to have compromised everything that connects to A before moving further. So that's the difference between N and OR. Yes, I also talked about the connections between the attack steps. And then, most importantly, we need to assign probabilistic distributions to those attack steps to express that effort needed by the attacker to move from one step to another. Of course, all the attacks, or at least that's what we want to achieve in the end, will have mitigations. Those mitigations are expressed by the defense attack steps. So those are special types of attack steps in MAL-based languages that are called defenses. By enabling them, you say that I mitigate against this attack vector by enabling the corresponding defense. And finally, we can also associate the attack steps with one of the following risks in the CIA categorization. So either it can be any combination of the following: confidentiality, integrity, or availability risk for each of the attack steps we create in the language. So those are the basic elements, and this is an example of how a MAL-based, very simple MAL-based domain-specific language will look like. So here we have the abstract asset vehicle, which it's abstract with the same way as on the programming languages, which means you cannot instantiate a vehicle, but you can use it to inherit from it. Because if you look below that, we have a car asset that extends from the vehicle. That means that the car asset, on top of the accessible and short circuit and immobilizer attack steps, it will also inherit the accessible and drive from the parent asset. So here, if we want to follow the connection of the attack steps, we can see that we can drive a car if it is accessible. And in the case that the immobilizer is enabled, this blocks the short circuit attack step. So by enabling this mitigation, we cannot short circuit a car and get it started. And then in the end, we see the association. So we see that a vehicle can be paired with one key. So the paired key is the association name, and the vehicle and the key are the aliases of the ends of the association. So yes, you see pretty much how very quickly and with a very simple example, how a MAL-based domain-specific language will look like. Now, let's talk about how how the first version of VehicleLang was developed. So VehicleLang, yes, it was based on MAL, but it was also based on what we now call legacy CoreLang, because we should not really confuse it with the current version of CoreLang. So what is legacy CoreLang? Legacy CoreLang is a core modeling language for generic IT infrastructure that is also MAL-based, and it includes basic components, assets actually, that are found in generic IT infrastructures like machines, networks, data flows, vulnerabilities, network services, and more. But it does not include complex assets like firewalls, intrusion detection, and prevention systems. So to develop VehicleLang, we didn't actually create everything from scratch. We were based on the main elements that were found in the legacy CoreLang, and we added the new elements that are found on the specific domain of vehicular infrastructures. And the method used to develop VehicleLang is actually the following. It is comprised of 4 steps and some loops. So first, a domain survey was done where we were interested in creating a feature matrix of all the assets that are found on vehicular infrastructures to validate that those assets selected from the research done. We did a Q&A session with a domain expert who we asked if we have everything covered or we need to include something more. Then a literature study for attacks that can happen on those assets was done. Out of this, an attack list or attack vector list was created. And that was the list of all the attacks we wanted to be able to model using VehicleLang. Then the actual development phase of the language started. It was, yes, based on the legacy CoreLang, and then the implementation of the new assets was done and the new attack steps and the associations needed to include, to merge them with everything that we had when the legacy CoreLang was done. And then here's the loop. So after we finish the development phase of every asset of VehicleLang, we did the same process as above. So step 1 and step 2 again to verify that we have covered everything correctly. And then we move to the next asset. After those loops were completed, we had to validate and verify the solution, which is the first ever version of VehicleLang. So the verification, the validation was done using test cases, and the verification was done doing reviewing sessions with other developers and a domain expert. So the overview is that VehicleLang currently models more than 45 attack vectors. You can see some statistics on how many of them are on each of the biggest assets. There are more than 41 assets modeled, and more than 90 attack steps. And also, a lot of test cases were created for the validation of the language. And the language itself is split in 4 smaller files to allow modularity and also to allow it to be easier to read. So if we want to see a diagram where we can see all the assets that are found in the language right now, this is the diagram. And you can see with the legend is actually only showing the colors here. But if you pay attention to the arrows, you can see that everything that has an arrow pointing upwards is inheritance, because this is a UML diagram, and all the other lines show how the assets are connected with each other. So those are associations. So for example, you can see that here the network service is actually inheriting from service. And if we look on this, the response, we see that a network service is associated with data flow with the association name response. So this is also the same happens also in the vehicular networks. Vehicle networks, we have 3 types of them: CAN network, FlexRay network, and Lee network. And then we have here the G1939 network is a subtype of the CAN network, because this implies inheritance. So those are the assets that are currently found in VehicleLang. And here's actually a small part of the actual language, and more specifically of the ECU asset. So you see that the connect, the access, and the attempt change operation mode are attack steps. The ones that start with an underscore are also attack steps, and the underscore means that those should not be visible to the end user, but are in the language because they help us connect attack steps. But many times the language is more complicated compared to what the end user sees, because some internal connections between attack steps are never shown to the end user, but are there because they're needed for the actual implementation of the attack vectors. And here the exponential distribution on the attempt change operation mode is the effort needed by the attacker to perform that attack step. Now, let's talk about validating VehicleLang, and in general, any MAL-based domain-specific language will be validated using test cases. Since MAL-based domain-specific languages until today are Java-based projects, we use JUnit test cases to validate them. And actually, we use 2 types of test cases. First, the unit tests, which are targeted in testing that the implementation done on the attack steps of a specific asset is correct. We also have integration test cases where we connect more than one asset with others, and then we test that the connections between the attack steps of various assets is as it should be. So the test cases are actually a way of testing if we have developed the language as we wanted. So here we can see an example. This is an integration test case because it involves more than one asset. So here we are trying to test a malicious transmit on a data flow transmitted over a neighboring network. So the attacker, this is the attacker, has physical access on vehicle network 1. And by having this, he is able to do denial of service, eavesdrop, and malicious transmit on the data flow that is transmitted over this network. And all those names that you see in the lines, like the DOS, eavesdrop, and malicious transmit, and the connect, are actually the names of the attack steps. So by being able to do those on the data flow, he is then allowed to reach vehicle network 2, because as we see here, the firewall and the IDPS systems are disabled. So those two things are actually the defenses, like I mentioned before, but here on this test case we are using, they're disabled. So by being able to reach vehicle network 2, he's then able to do a malicious transmit on the other data flow, which is transmitted over vehicle network 2, and he is also able to connect to this listener ECU that is connected to this network. So that's a graphical representation of how a test case looks like. Behind that, you actually have Java code. So you first have to instantiate the instances of the assets you want to have in the model. Then you have to create the proper connections, which are the associations. And then you do some assertions, which assertions are based on your belief of what should happen if you have this scenario. And then if you run it during the compilation of the language, all the test cases are also run, and you get output like the one on the right, where you see if the assertions you made are satisfied or not. So if you have created everything correctly in the model, and you have done also everything correctly in the language, like the connections between the assets and the implementation of the attack steps, then your assertions should be verified by the simulations. If the assertions are not verified, then the first probable cause is that you have done something wrong in the model on the test case. Or if you have done everything correct in the model, then it means that during the development, something went wrong and you are not reaching what you should reach because of that error. So you have to go back on the development and verify that you have done it correctly. So that was the validation. What about evaluation? So with evaluation, sorry. Okay, so with evaluation, we are talking about how useful a system is to the end users. So to evaluate VehicleLang, we can do it with two ways, or at least this is what we have done so far. So first is by using domain experts as testers of the language. So we, after the first phase of development is done, and the language is ready to use by the end user, we give it to the domain experts that will be acting as testers, and we ask them to create models, study the simulation results, provide feedback based on the results they get, and based on that feedback, we can improve the language. And then we can do another round of that until the testers are satisfied of the end product. Another way of testing for evaluating a MAL-based domain-specific language and VehicleLang in this specific case, which we followed, is by performing a Feigenbaum test. Now, a Feigenbaum test is actually very similar to a Turing test, which is a game between a domain expert and a computer or expert system, as it is called in the literature. And the main question that the human judge has to answer is, can he determine at a better than chance level if the output he's seeing is from the human or from the computer? So we are actually playing a game and we have a judge, and we make the humans do the same thing as the computer, or the computer do the same thing as the humans, and we ask the judge which one is which. So in the case of VehicleLang, we have selected, we have created a model that was similar to what we have in real vehicular infrastructure. And then we have selected 9 different attack goals that both the experts and the machine will have to reach somehow. And then we had 6 test subjects, 3 experts and 3 non-experts, and we asked them to actually create attack paths, which are the steps you need to follow on the model to reach the end goal, those 9 different end goals. So one attack path was created for each of the attack goals. VehicleLang also simulated those, and then the judge, which was a domain expert, had to rate each of those attack paths using a 1 to 5 Likert scale. Now, the Likert scale is what you typically see from in many questionnaires, where 1 is the I do not agree at all, and 5 is the I strongly agree. So the question the judge had is had to answer using this scale is that this attack path I see is reasonable and correct. So 1 is the completely unreasonable, and 5 is the I strongly agree with this attack path. And as we can see on the results, if we take attack 1, for example, we see that experts A and B were achieving the highest score based on the judge. So they got a 5. VehicleLang also got a 5, and expert C got a 3. So that means that expert C is either new in the domain, or he didn't do everything correctly based on the judge. And then, for example, if we look at another attack, like attack 2, we see that expert A, B got a 4, while VehicleLang got a 2, which is the same as expert C. So we see that based on the attack goal selected, VehicleLang achieved either equal or worse results than the experts. But again, this is the evaluation for the first version of VehicleLang that allowed us to make improvements on it. Now, if we compare it, of course, with non-experts, we can see that every time VehicleLang achieves better, because it's not targeted to be used by non-experts, of course, but if we are better than non-experts, then that's a good start at least. So to conclude, I would like to highlight the contributions of VehicleLang. So VehicleLang is a probabilistic modeling and simulation language for vehicular cyber attacks. It was initially developed as part of my master thesis at KTH, but after that it was further being improved and developed based on the feedback we have gotten. So this version I showed you here is not the first one, but some methods I mentioned were followed for the first version. So is also a foundation of still ongoing research work. And the ultimate goal is that it could foster vehicular threat modeling from the manufacturer side. And yes, it's also being validated through reviewing sessions with domain experts. And the goal is that if the domain experts start using the language, it will also self-improve, because it's better to have users from the industry rather than having researchers trying to catch up with what's happening in the industry. And since this is an open source project, anyone can contribute to that. So that was all from me. And next up, Joar will show you how VehicleLang can be used in action, actually, to create models using tools instead of code and see the results in a beautiful way. So thank you.
Yes, so it's time for me to show what this looked like when we use it within this securiCAD enterprise solution. Some of you might have attended the previous webinar that I was presenting, and in that case, you know what this securiCAD Enterprise solution is about. And as Sotirios has explained so far today, we have a probabilistic modeling languages. And those modeling languages are really, well, the purpose of them is to define which types of assets that can show up in a specific environment. And they differ a bit from industry to industry. And also how they interconnect, or what kind of relations they have to each other. It could be applications and data and users and networks and so on. Then, of course, what are attackers expected to be able to do once they sort of get a foothold in one asset in the architecture? What is then reachable from that position? So if we look at, to begin with, the modeler, so this is a VehicleLang Cherokee model because it's inspired by this GPAC that's now classic, I believe. So we go to the modeler here, and in this one we see that we have these objects with their interconnections. So we have this canvas, we have ECUs, and we have a lot of controllers and things like that. And as you, of course, notice, I'm this non-expert person, so I know a lot about many things, or a little about many things, rather. So for these different, if you remember from the CoreLang presentation, which is the more let's say industry agnostic modeling language, we had applications and we had networks and so on, but we didn't really say that we had some what kind of implementation these applications were based on, and we didn't say that for networks, for instance, that it was specifically a TCP/IP network. It was more about what can you do with a network? Well, you can gain access to it. You can connect to anything that is related to that network. So it's more about reachability, really. So we right-click on these ones. We go for preferences, and here we see the so-called attack steps. And these are the operations that an attacker is expected to attempt and might succeed with. And some of these require that you have succeeded with other operations before. So, for instance, this connect is an early attack step in the context of this asset. But it likely requires the attacker to really reach these positions to be able to make that connect. And as we can see in contrast to the system or application object that we saw in the more general CoreLang, we have some very vehicle-specific attack steps here. So it's talking about firmware, it's talking about ID control. Gain network access is not really specific to this, but gain LIN access from CAN, that is more of a vehicle-specific thing. Then, if these are the things that the attacker would like to achieve, then we can open this defenses section here. And here we see something called message confliction protection and operation mode protection. So these are the defenses related to this type of asset. If we go to another type of asset, this network here, we see that we have access UDS services. We have eavesdrop and denial of service, which is very network general. But we have J1939 attacks and so on. So it's a mix of vehicle-specific operations, because there are different techniques here that's available depending on or because of the specific implementation. But there are also other goals that the attacker would like to achieve, like eavesdropping this communication here, or succeeding with other things here. Man in the middle, for instance, it's not specific to canvases, but it's very applicable to canvases. Let's see if we have some defenses. Bus of protection. Yeah, I don't know by heart what that is. But it is a CAN bus related protection, and I believe several in the audience nod their heads right now. So what we have here then is that, like with any other language, we have the attacker's entry point. This one is connected to something called Internet on Star, and this is not really maybe on the vehicle itself, but it's the bridge over to, let's say, the workshop or something, an external connection really. And if I would like to have this attacker connected to some other location, I could, for instance, connect it to firmware here that is representing, well, sloppily expressed, the application or the release. I would be modeling a supply chain attack, really. So the scenario would then be not that really that the attacker has gained all that much access to the vehicle, but that the attacker has the possibility to introduce its own code. And then how bad that would be to, for instance, the steering system over here. It depends on, or this steering actuator actually. It depends on how difficult it is to travel from this position over to this position. As we can see from the picture, it doesn't seem that difficult, but it might be cases where the attacker gain access to one part of an architecture and then have a bit of work to do in order to proceed onto other parts. That's the separation that was bridged in the Jeep Cherokee attack, by the way. So if we look at the different objects, these are the objects that are defined in the current version of the VehicleLang, and we can take a look at where we can find and review the inner definitions of these ones in a while. But if we skip out of here, we see that we can run a simulation on this model to see that, okay, we had the attacker in the star network at the bottom. What is expected to happen next? Well, the attacker is expected to try to find ways to proceed in the architecture, really. So if we go for this report here, we have this initial simulation that has been run in the same way as I was showing the previous time. Well, I can summarize that. securiCAD is taking this model, setting up an attack tree containing the theoretically possible different paths from one position to another in the model. And then depending on the different attack steps and their difficulty, this is expected to be, well, some jumps, so to say, are easy and others require some effort. And then what we get is a so-called critical path, and that is the expected easiest track from one location to another. So in this case, we see denial of service is the attack step that we are interested in. On the asset in the model called CAN-C. This is the central CAN bus, I believe. And we can take a look at the critical path. Here we see that we have the attacker's entry point going to internet/onstar. That is the object name. and access is the attack step. This was our what-if scenario, because we had the attacker connected to that location in the model. What is expected to happen next? Well, as a direct consequence, because of intended architectural use, if you have access to this network, you are supposed to be able to connect to the dbus service and to connect to the Uconnect radio module. If you do that, then you will be able to go over this track over here. And likewise, another path that is equally feasible for the attacker is to go over this dbus service network here, but it would require you to use a connection vulnerability exploit. And if you have that, you can compromise something called a super user, and that will bring you to the into the same track here. And here we have another set of different industry-specific things. We have forwarding, connect, and attempt change operation mode. Attempt change operation mode, I would say that it from a more generic perspective would be the same thing as modifying the access rights of an application. So I can also disable this auto layout, so I get a different layout of this, and showing the layout is not that interesting, but what I would like to show is that regarding this operation mode, the possibility to change this operation mode, it's dependent on the operation mode protection defense that might or might not be enabled on this IOC asset here. So that means that the reason that this one is not enabled, this defense here, is it could be that it is actually not present in reality, but it should be present. It could be due to versions in the implementation, but it could also be that, suppose that it is due to that this IOC doesn't support operation mode protection, then it will show up as a part of this successful track from the star network over to the CAN-C. But here you could really change the probability of this one. You could enable this in the model to see how much is it going to, what's the expected outcome of enabling this. Then you could make a decision on if this should be enabled. And if we think about IT systems and so on, this is sort of similar to, enabling hardening a system and things like that. But when it comes to the more industry-specific a technical solution or an architecture becomes, the more difficult, seemingly easy mitigations might be, because updating something might call for a calling in of a whole series of cars. If we think about power distribution, it might be have systems that are out of date because the hardware is not supported on later versions of software. So that means that in worst case, you might have to rebuild a couple of power distribution stations and so on. And on the other end of the scale, it's about enabling automatic updates. So yes, we could also see that in some cases, I don't know if that's the case for this small example model, but for some cases we have alternative attack paths, because this is the expected easiest track. So if this is track or chain of operations is going to be successful, it's expected to be the most straightforward for the attacker. And if we increase the level of detail here, we see that no, we don't have any additional attack paths. So this means that if we would block this or cut off that, making sure that we remove this possible vulnerability, then the attacker is not expected to have any additional attack paths here. But that is from this starting point. And if we would have another entry point for the attacker, so it means that the attacker wouldn't sort of try to connect to this this vehicle from this OnStar network, but instead would focus on maybe compromising source code that is sooner or later going to be committed and hopefully undetected into some seemingly less critical component of the car, then the attacker might actually be able to gain access to this area from start. So that's about attack paths and the different ways of, yeah, let's see if we have suggested mitigations for this one. Yeah, it's on only one suggested mitigation here. It says either prevent diagnostics mode after vehicle starts moving or allow diagnostic mode only after some physical changes is done on the device, on the vehicle. So as we can see, this is a description of the rationale really for enabling this defense on this IOC asset here. And that connects back to what Sotirios was explaining about the inner mechanics of VehicleLang. So how can we suggest something like this? Well, it is part of the attack path, but it is really connecting back to what VehicleLang look like. And as Sotirios mentioned, the VehicleLang is an open source project, mallang/VehicleLang. And if we look at the code here, we see that we have different assets. And here we have asset machine extends physical machine. And what can you do with a machine then? You can connect to it, you can authenticate, you can gain authenticated access and so on. And there are, to some of these, we have defenses as well. I don't find any defenses at the moment because they are prepended with a hash. Yeah, here we have one defense, which says firmware validation. And here we have a description, and firmware validation is something that if this is in place, it will be more difficult to bypass firmware validation, but it might not be entirely impossible. So yes, and also the difficulty of certain attack steps to be succeeded. In this case, crack secure boot. This is an attack step which has got a probability distribution to it. I don't know if you can see this because it's kind of small, but I will read it. It says exponential 0.1. And this is because we have found out that this crack secure boot is not going to be a direct consequence of something else, but instead it should have a probability distribution to it. Then, if we look back at the model again, I would also like to think a bit more about this inheritance thing, because what we see here in this picture here in this model, it is a high-level model of the essential components within a vehicle, and then we have the attacker starting point and so on. But actually, when we think about a vehicle being connected to different services for, let's say, updates and so on with a vendor, or if we think about a situation where this vehicle is connected to a workshop for maintenance, then this environment suddenly becomes part of a larger IT environment. And then we have really, in a way, left or bridged between the vehicle architecture over to the more traditional IT architecture, really, of the workshop or the vendor. So that means that it would be good to connect this architecture to a CoreLang defined architecture showing the, let's say, the office zone and things like that of the workshop. And the way to do that is to really combine these languages, and there's an ongoing work at the moment for combining languages. So in this set of modeling objects here, we see that they are all related to vehicles. But it would be possible to also add other asset types here that are not specifically vehicle related, but could be CoreLang related. So a couple of times I've mentioned attack steps, which is the interesting part here. Attack steps that might as well be related to any network. So let's say that you have, for networks, you have a man in the middle and denial of service and so on, and gaining access to networks. And for data flows, then you have the transmit response and deny operations. It doesn't automatically say do this and that technique within a TCP IP context or within a CAN bus context. It says the operation the attacker would like to do is to intercept with the traffic. And then, of course, depending on which network you are targeting, if it's a CAN bus or TCP IP network or token ring system, then you need to use the proper tools. But that's less interesting other than expecting that the attacker has a pretty neat toolbox. So the way to do that is to really let networks and other important denominators, so to say, like software and things like that, inherit from basic classes in CoreLang. That is something that is being investigated currently. It is also not really related to vehicles, maybe, but if we think about a similar phenomenon within the sort of Internet of Things area, there are services popping up that are cloud-based but target IoT. So, for instance, this Azure, they have released this IoT hub, which is really an Azure service for making IoT devices, definitely on-prem, be available and representable in the cloud environment. So that's also a hybrid thing that is coming up. Yes. I believe that that was what I would like to present around this, really. Yeah. So this is the VehicleLang starting from Sotirios master thesis that is shown in live action.
All right, great. Thanks, both of you. So there are some questions that have popped up. But before we go to those, just to be sure that everybody gets this right. So there is MAL, right, the meta language, that provides kind of the syntax or the semantics or some operators. And then using this syntax, you can create other specifications for specific domains. And an example is VehicleLang, right? This is how things work, right?
Yes, exactly.
Yeah, I mean, if you look at this code, then a simple way to put it is that the Metatag language is defining the different operators here. We have OR steps, we have AND steps, we have this arrow saying that this leads to something else, and we have a hash character here saying that this is a defense. And what does a defense do? Well, it makes something more difficult than just a straight next step. So MAL is defining the relations between these ones, but the core lang and the VehicleLang and ICS-lang and ASRG-lang and other kinds of languages, they are the actual definitions that you put in here. But ampersands and pipes and stuff like that is the MAL specification. Or do you have a comment on that, Sotirios?
No, I think you covered it.
All right, and at some point you mentioned that you can convert these languages into Java code. I guess this happens with some kind of a MAL compiler of some sort, right? That compiles it
Exactly.
into Java. Okay.
So every domain-specific language that is MAL-based is also a Java project, and in order to create the actual executable file that runs the simulations, you'll have to use the MAL compiler, which is also Java-based, at least the current version. There are also plans in moving to Python and having everything expressed in JSON files, which will be more universal and easier to handle, but this is the future. So right now we have a Java-based compiler in which you put through the, if we call it the MAL specification, which is the code, the code of the language, and then you get you either get simulation results if you use the Java framework, or you get a jar file which you load in securiCAD in order to create models with the GUI interface.
I see. All right. And so if somebody wants to work with all these things, I mean, where can they find the compiler? And yeah, how can we jump into this?
Yes, sure. Allow me to screen share. So I think you see my screen now. Most probably, yes. Okay, so there is, we have a web page, mal-lang.org, where you can find information on how to get started on using MAL, and also see some other examples of MAL-based domain-specific languages. So this is the web page. And we also have an organization on GitHub, the mal-lang organization, under which you can find both the compiler and also other languages developed using MAL. And here you can see example VehicleLang, the compiler. Then you have CoreLang, which is the new version of the basic IT modeling language. And then you also have some other projects that are MAL related. So everything related to MAL, you can find it actually on the GitHub under the organization, and informations in text form, you can find it on the website, the mal-lang.org.
All right. Great. So another a question that also came up in the previous webinar. In vehicles, as you mentioned, there are parts, internal parts like ECUs and then the canvas and all these things. But in a motor vehicle, there's a lot going on also outside of the vehicle, in the periphery or even further ahead. So there's also, cloud-based infrastructure supporting it. There's V2X infrastructure in place and other things.
Yes.
You mentioned something about Golang and then other languages and other domains. Is there some other languages, let's say, some other such specifications like VehicleLang that can be combined with VehicleLang so that they can cover more of this of the vehicle domain of today instead of just the really hardcore stuff?
Yes. So the vision we have created over the years after the VehicleLang was developed is that we are going towards the MAL-based ecosystem of domain-specific languages, where you will have a collection of domain-specific languages that cover from basic IT elements, like the current version of CoreLang does, and then there are other languages will be built on top of CoreLang and provide a more specific, a more narrow point of focus into smaller domains like the vehicular or the power domain. So we can think of that as a tree where we have CoreLang in the center, and then we have branches inheriting from CoreLang and covering more specific and smaller domains. The current version of VehicleLang was developed before CoreLang, the current version of CoreLang we have, so it's not based on CoreLang and cannot really follow this ecosystem idea without being modified. But of course, if we modify it, which is actually a plan, to be based on the current version of CoreLang, then it will be part of the CoreLang ecosystem. And then the external parts, like the cloud communications that are happening for telematics, or the communication with the smart city nodes in the vehicle to infrastructure scheme, can be modeled with a combination of, let's say, VehicleLang, CoreLang, and maybe some other language that is specific to the cloud, like, for example, AWS-Lang, which is the language that models everything on the Amazon Web Services infrastructure.
Right. So this is more like a goal for the future, right? Right now it's kind of hard to mix those together in the current form of VehicleLang.
It's hard because we haven't yet finalized CoreLang. So if we finalize CoreLang, which we of course have the first version of CoreLang, the first stable version is available on the MALLang organization repo. But if we finalize everything that we want to have tried, then we will be ready to start adapting the existing languages that were developed before CoreLang to follow the CoreLang idea. And this is something that is planned to happen really soon, because we're actually in the last steps of validation and evaluation of CoreLang. So we are hopeful that this will happen very soon.
All right. Great. So another question is, if you're aware of other similar languages or other projects that have a similar goal, develop a modeling language for the vehicle domain, and how they compare to what you're suggesting here.
Mm-hmm. Okay, so I am aware of other attempts to create models and run simulations, cyber attack simulations on domains. Most of them, however, are focused on the IT domain, like Strada or Tara. You can do some workarounds to also model the vehicular domain, but none of them is actually built for the vehicular domain. So most probably you will be missing some specifics to the domain. And also, I do not think that any of those is actually a way to probabilistically generate simulation results.
Mm-hmm. All right. And final question is about the industry usage of VehicleLang. You mentioned also that you cooperated with some of the industry to validate VehicleLang when it was developed.
Mm-hmm.
can you give some more details about the industry that was involved?
Sure, yes. So when during the development phase of Corla or of VehicleLang, we had some contacts in Scania where they helped us detect the basic assets that can be found on the domain we want to model. And also we did some validation work with them with interviews. And also some people from AUTOSAR were involved in discussions, mainly, not providing feedback when the development was ongoing.
Right. So could there be some flavor of VehicleLang that could be described as AUTOSAR Lang or something?
There was an attempt back when I was a master thesis student. There was an attempt to create an AUTOSAR Lang that will be specific for AUTOSAR-based vehicular infrastructures. But I don't really know how far this project went. But interest was there.
But I guess, given the goal of VehicleLang, it would be possible to use that to describe AUTOSAR.
Yes, true.
infrastructures.
Since AUTOSAR is just let's call it a framework of how things can be done. Yes, I strongly agree that VehicleLang can be used as the foundation.
All right, great. So there are no more questions from what I can see. So we can wrap up for today. Thanks a lot to both of you, both Sotirios and Joar, for your presentation. To the audience, see you in an upcoming webinar next week. Thank you. Bye-bye.
Bye-bye.
Bye. Thank you.